So today, the plan is that we're going to study linear differential equations of higher order. We started with this last time. We will tell something more about this. So, linear differential equation of higher order. We will say something about existence and uniqueness of solutions. There is one nice theorem checking if n solutions are linearly independent, and it's called Wronskian determinant, and it has a nice proof. So we will just go over this proof because it is on the collision between linear algebra and what we already know from differential equations about solving differential equations, and we'll see a nice trick how to check if the solutions are really linearly independent using this Wronskian determinant. It's a common name in the theory of differential equations. So it's right that you see at least the idea of the proof. So this will be the first thing. So the buzzword here is Wronskian determinant. Then the second thing will be to study non-homogeneous differential equations, because non-homogeneous differential equations are the ones that appear in real life. So non-homogeneous DEs, and we will see two techniques to solve such a non-homogeneous DE. One technique is just by guessing, and the other is by variation of constants. We did this for when we have differential equation of first order, but we'll generalize this technique to second order differential equations. Second order differential equations are the ones that appear in practice. So one technique will be guessing, and the other will be variation of constants. So for one differential equation, for a differential equation of first order, it's really easy. Just you solve, if you remember, you solve the homogeneous part. In the homogeneous part, since it's a first order differential equation, you have a constant, and then you replace the constant by a function and plug into the initial differential equation, and you can solve from this function. However, in the second order case, you still get the two-dimensional solution of the homogeneous part, and then you replace constants with functions, and then you plug into the initial differential equation, and it doesn't go directly as in the first order case, but you have to do some reduction, and we will see what reduction. So it's the natural reduction, and it really works. So this is the second thing. And at the end, which will be the final topic of this course, we will study applications in real life, in real life examples. And the most studied case is vibrations, so vibrating pendulum. We'll see the application of all possibilities. Either we have only homogeneous vibration, and then we'll also add some damping factors, and at the end also the impact of force. based on those 4 cases, we'll also see different phase portraits. So last time we studied phase portraits, and in this vibrating pendulum, we will see all 4 cases. Okay, this is planned for today. Maybe we won't do all of this, but what remains will be done next time. But next time we also start with preparations for the written exam. Okay, is there maybe any question? Okay, let's start then. So let's just write down linear differential equation of higher order. So LDE of order n. It's a differential equation which has one independent variable and one independent one. And since it's of order n, this dependent variable appears to all derivatives up to n. So we have n derivative plus then some function of t times n minus first derivative and so on. So we have a1t times first derivative of our function. And at the end, so the part without the derivative. xt, and this is equal to some function of t. So this is a non-homogeneous linear differential equation of order n. Okay, i's here are functions of the independent variable. And also f is the function of the independent variable. And here this I is an interval on which we are searching for the solution. So I is it could be also the union of intervals, but it doesn't make sense to say that I is a union. It's better to just say that it's a compact interval. And if we would like to find the solution on the union, then we just find solutions on each of the intervals in the union separately. So in general, instead of I, we would take a domain in R, but it makes sense to just say that I is a connected domain, so it's an interval, and study the solutions only on this interval. So what we know from the theory by now, how many parametric solution of the homogeneous part do we expect? Yes, n parametric, yeah. So by how do we argue about that? So let's say that we started with such an nth order differential equation. We don't know anything about that. We don't know that we expect n parametric solution, but we know something about systems. So how do we argue that we really expect the n parametric family of solutions? What can we do? How do we really get to some of the solutions? What can we do by what we know by now? So we know how to solve systems of first order differential equations. And how would we translate this nth order differential equation to the system? Yes, this is the trick. Yeah. So what we do is to introduce new variables. We've seen this trick 2 times. We introduce new variables. X1 is just our function x. And then x1 prime is then x2. x3 is x2 prime, and so on. So those are new variables. We need n new variables. We just take derivatives of the previous ones. And you see the differential equations are just those from the second on. And here we didn't use our differential equation yet. So this is just some algebraic trick by now. It's the same for all differential equations. But now we see the impact of our differential equation when we take the derivative of xn. So now we take the derivative of xn. And what is the derivative of xn? This can be seen from our differential equation. For our differential equation, we start with, because what we did for xt, we introduced the variable x1. So this is a function. And then prime of x is then x2, and so on. And n minus first derivative of x is actually xn. And then nth derivative of x is actually derivative of xn. And from here, we get the differential equation, which is specific. So the differential equation in the system, which is specific to our initial nth order differential equation. So xn prime is then minus an minus 1 of t, and then xn minus an minus 2 of t, xn minus 2, and so on. x1, sorry, x2 minus a0 dx1. And we also shouldn't forget about the non-homogeneous part, ft. And from the existence theorem for systems of differential equations, we know that we expect n-dimensional family of solutions. So this means that we also expect n-dimensional family of solutions for the nth order differential equation. So from the theorem on existence and uniqueness of solutions for the systems of first order differential equations, we know that there are n linearly independent solutions for the homogeneous part. Which means that there are also n linearly independent solutions for our initial differential equations of order n, which implies the same for our nth order DE. So here I was cheating a little bit. Did we really study the existence and uniqueness theorem for systems of linear differential equations? No, so the theorem which we stated was only for one differential equation, but in fact, everything, this theorem which we stated generalizes with the same statement to systems. So we have the same, instead we stated this theorem only for n is 1. We stated, in fact, we stated this theorem a few weeks ago. Only for one first order DE, but the statement and also the proof, we looked at the idea of the proof, and the statement with the same proof generalizes to systems. So to remind you, we had the rectangle, we had y prime is f of xy. This y was just a function from the interval into real numbers, which we are searching for. And so we were searching for the solution on the rectangle. So it had x minus a, x naught minus a, and then x naught plus a. And then this was in the x-axis, and in the y direction, it was y naught minus b to y naught plus b. And the initial condition was that the solution should go through this point, x naught, y naught. So we are searching for the solution of this differential equation under the initial condition that y of x naught should be equal to y naught. And the theorem stated that the solution exists and is unique, maybe not on the whole interval, but at least on some subinterval. So it was, so the statement said that the solution exists for x, not maybe between, for x, not maybe in the interval between x naught minus a, but for x in the interval between x naught minus alpha and x naught plus alpha. And we had three conditions on alpha, where alpha is minimum, between a, and then we had here two other constants which were dependent on f. So I won't state them explicitly again, but those constants, so c of f, c1 of f, and c2 of f, those are constants dependent on f. So one was the constant which assured that y really stays within this rectangle. So c1 of f was the constant which really ensured that y doesn't go over the upper or the lower side of the rectangle, while c2 was a constant which really ensured that the solution exists. It was the constant which assured that some operator is a contraction. If you follow the proof with y and f being vector functions, the same works. So the same works, the same proof works for for the system. Of course, then, so here we have a rectangle. When we have two dependent variables, we don't have a curve. We are not searching for a curve in plane, but we are searching for a curve in the space. So it would, instead of a rectangle, we would have a cube. And if we have three variables, then three dependent variables, then we would be in R4 and so on. So the solution is a curve, only that it lives in Rn if you have n dependent variables. Okay, so we really expect n-dimensional space of solutions for the homogeneous part. So the homogeneous part of our DE and order DE is n-dimensional. So x of t is some constant c1 times x1 of t plus c2 x2t and so on. This is the solution for the homogeneous part. These are all solutions for the homogeneous part. Those C1 and C2, C1, C2, and Cn are parameters. So how would we determine the value of those parameters? What we need if we want specific solution, how do we determine what we need to determine the parameters? Some initial condition, yeah. So if we look at this upper picture, the initial condition was this green one. So y in point x naught should be y naught. Here, the initial condition would be that the value of the vector x in some point t naught is given, and so we get n conditions from which we can determine those c's. And to solve the differential equation, also taking into account the non-homogeneous part, which is the function f, if you recall, we had this function f, which was the non-homogeneous part of our DE. So to determine the solution taking into account also f, we need some particular solution. So x p of t is a particular solution which solves DE taking into account also f of t. So the space of all solutions is then x of t is sum of the solution of the homogeneous part plus the solution of this particular part. In this, the solution of the particular part is really any of them. So as soon as you find one solution of the DE, all other solutions are of this form. The solution of the homogeneous part plus this particular solution. So it really doesn't matter which particular solution you find, all solutions will be of this form. So is this clear, or is this difficult to see? How do we see that it really doesn't matter which particular solution we find? It suffices to find one of them. So how would you prove that this is really, all solutions are really of this form? So if let's say that xp1 is, or I will write 1 in the exponent. So xp1, oh, maybe this is not a good choice because it could mean that it's the derivative. Let's write xp, comma 1 of t into xp2 of t. Let those be two solutions, two particular solutions of our dE. So what we claim is that, since we claim that all solutions are of this form, we claim that xp2 of t is equal to some solution of the homogeneous part plus xp1 of t, where y of t is the solution of the homogeneous part. So this is what we claim. So is this difficult to see, or is this clear? How would you check that this is indeed true? So you're given two particular solutions, and we are claiming that one of them is just the first one plus some solution of the homogeneous part. So how would you check this? We can rewrite this this condition by just putting this particular solution on the left-hand side. So we have the difference of the particular solutions is some solution of the homogeneous part. So those two facts are equivalent. If we say that one solution is another solution plus some solution of the homogeneous part, this is the same as saying that the difference of those two solutions is the solution of the homogeneous part. So how would we check that the difference of the particular solutions should really solve the homogeneous part? How would you check this? It's easy. You only have to observe the initial differential equation. Yes, that's true. So let's return to our differential equation. So this is our differential equation. So we are claiming that we have two particular solutions. So we plug in xp1 of t for x. We get that xp1 must satisfy this differential equation. So instead of xt, we plug in xp1 and so on. And when we plug in xp1 into our dE, on the right-hand side, we get f of t. We do the same with xp2. So again, when we plug in xp2, on the right-hand side, we should get f of t. So we get two differential equations with two solutions. And if we subtract them, what happens on the left-hand side, we get xp1 minus xp2 and derivative plus an minus 1 times xp1 minus xp2 and minus first derivative and so on. So on the left-hand side, we get the same as if we plugged in for x, the difference between xp1 and xp2. While on the right-hand side, we get ft minus ft, so we get 0. Which means that the difference of the particular solutions solves the homogeneous part, which means that, which proves what we wanted. So this is in fact what we were proving. So xp2 minus xp1 solves the homogeneous part of the dE, which means that it should be this yt, because we said yt is some solution of the homogeneous part. So plugging in xp1 and xp2 into the initial dE, and then subtracting those two, subtracting both of them, we get 0 on the left hand, on the right hand side, and on the left hand side we get the expression where we plug in xp2 minus xp1 for x. Okay, so now we know that there should really be n linearly independent solutions of the homogeneous part. So we expect n linearly independent Now, you know this notion of linear independence for vectors. So what does it mean that vectors are linearly independent? So we have v1 up to vn are some vectors. In some vector space, in the vector space V. In linear algebra course, you probably studied mostly finite dimensional vector spaces V. But in our case, our vector space is the space of continuous functions on the interval, which are n times differentiable. So because we are searching for, when we are solving dE, we are searching for functions which satisfies this dE. And if the function satisfies this dE, it must be n times differentiable, which means that our V is this space C, and usually we write Cn of I. This n denotes the number of times the function must be differentiable. This I is an interval. So Cni, this is the space of functions. So functions on I, which are n times differentiable. And we usually we are usually searching continuous functions. So let's also add this continuous. So continuous functions on I, which are n times differentiable. Okay. We have n vectors in some vector space. Can someone tell me what does it mean that they are linearly independent? Yes, but how do we check that vectors v1 and vn are linearly independent? What relation should they, what algebraic relation should they satisfy? That would mean that they were perpendicular. They don't need to be perpendicular to be linearly independent.
We can express any of them without the other.
Yes, yes, this is one equivalent way of saying that. But just putting this sole vector on the other side would give us another equivalent expression. So if you have some linear combination, let alpha 1 v1 plus so on plus alpha n vn be equal to 0 for some alpha 1 up to alpha n. What can we infer about alphas if v1 and vn are linearly independent? They all need to be there, yeah. Which means that we cannot express in other ways. This means that we cannot express one of them, one of the vectors with the others. So let this linear combination be 0 for some alphas. v1 up to vn are linearly independent. If alpha 1 up to alpha n must all be equal to 0. Yeah, and Nate also answered in the chat describing this equivalence. Okay, this is linear independence for the vectors. And now we plug in, we're claiming that we are searching for n linearly independent solutions of our differential equations, which in our case means, so in our case, alpha 1 x1 of t plus and so on plus alpha n xn of t is equal to 0 should mean, so in our case, if we have some linear combinations of the solutions of our DE, the solutions of our DE are x1 up to xn. So we claim that it follows that alpha 1 up to alpha n should be 0. So if this is 0, then alpha 1 up to alpha n should be all equal to 0. Okay, this 0, how do we understand this 0? So on the left-hand side, we have a linear combinations of the functions. So this left-hand side is in fact another function, a function from the interval I to real numbers. So how do we have to understand this 0 on the right-hand side? So because we are claiming our vector space is now the vector space, we said that our V is the space of continuous functions which are n times differentiable. And now we take some linear combinations of the solutions of our DE and say that it is 0 in this vector space V. What is the 0 in the vector space V? Yeah, origin. origin, as Nate says in chat, but what is the origin in the space CNI? So what is the neutral? The origin in the vector space is the neutral element for addition. So which function doesn't change? If we add some function to any other function, this function doesn't change. Which function is that? So which so we lost connection for some time. Now we are back. So which function is a neutral element for addition in the vector space of continuous function on the n times differentiable continuous function in the interval I? Homogeneous solution. So let's write our function. So let's say that we have only not the system, but the function, and our interval is that one. Let's say that this is our interval, and here we have our vector space are some functions here. So f1, f2, f3, and so on. So which function is neutral element? So in this vector space, we are making sums of these functions. They all live in our vector space. So which function is such that f1 plus g is equal to f1 for every f1? What is g on this picture? 0, yeah, 0. So this 0 is in fact the function which is constantly equal to 0 on this interval. So this 0 denotes the function which maps every t to 0. So on the left-hand side, we have some linear combinations of solutions. We sum them together, and the solution is a function, is precisely this black function. And recall that those x1 up to xn, so those are functions, yeah. Yes. Yeah. So it maps into real numbers, and 0 is also a real number. So the codomain is are real numbers. So the function, if we say that function maps from I to real numbers, this only means that every t, f of t, belongs to real numbers for each t from the interval I. So, and if you write this function 0, it maps from the interval I into real numbers by the rule that 0 of t. So here we can write this 0 as bolded so that it's really a function. It maps t into 0 for each t from the interval I. It's really, so this green, this black function is really a function which maps into real numbers. It's a constant function. It's a constant function with value 0 all the time. Okay. Now we will form this Wronskian. I've told you that the Wronskian is a very important notion in the theory of differential equations. So a Wronskian of the solutions x1t up to xnt is an n by n matrix formed by x1 up to n minus first derivative of each of these functions. So is an n by n matrix, which looks like that. So in the first column we put x1, and then x1 prime of t, x1 double prime of t, and so on, xn n minus x1 n minus first derivative of t. So this is first column. And then x2 of t, x2 n minus first derivative of t, and so on. And this is so-called Wronskian. It's usually denoted by W of x1 up to xn. This is, in fact, it is a, so what's the domain? Let's see if we understand this correctly. What's the domain? Let's write here the domain and the codomain of this Wronskian. So the domain is what is the argument, what we plug in into Wronskian, and the codomain is where it maps to. So what we will write here as the domain. What is the argument? T, yes. So the domain is I. So in fact, the independent variable is T. And what's the codomain? So we see we have this matrix. So it has n columns, and each column has n entries. So it's in fact n times n matrix. So it's in fact a matrix function with n columns and n rows. And recall that we have x1 of t, x2 of t, and xn of t being the solutions of the homogeneous part of our differential equation. So now we have two notions of linear independence. What does it mean that what does it mean that we will have two questions? What does it mean that V1 of t up to Vn of t are linearly independent? This is the first question. And the second question is, what does it mean that the determinant of the Wronskian calculated in some point t naught is equal to 0? And then we will see the connection between question 1 and question 2, which is specific to nth order differential equations, and is a very important part of the theory. So question one, what does it mean that those vectors, which are in fact vector functions, because for each t, we get v1 of t is some column vector, and then v2 of t is another column vector, and so on. So what does it mean that they are linearly dependent? Question one. As above, as we said above, this means that alpha 1 v1 of t plus so on plus alpha n vn of t is equal to a vector of only zeros, implies that alpha 1 up to alpha n are all zero. Okay, this is just the definition of linear independence, which we recalled above. And now my question for you is, what does it mean that the determinant of this Wronskian, when we calculate it in the point t naught, is zero? What does it mean? So when we have a square matrix, if the determinant of the square matrix is zero, what does it mean for the matrix? For the columns of this matrix?
They are not linearly independent.
Yes. So if the determinant of W calculated in some parameter t naught is zero, this means that vectors v1 of t naught up to vn of t naught are not linearly independent. So determinant of W of t naught is zero implies this is equivalent to saying that v1 of t naught up to vn of t naught are not linearly independent. So the question, another question is, question 3 is, if determinant of W t naught equals to zero, does this imply that v1 of t up to vn of t are linearly dependent? So now we know that the solutions v1 up to vn, when computed in some specific point t naught, are linearly dependent. Does it mean that v1 of t up to vn of t are also linearly dependent? Which notion is stricter? So if you have matrix with n columns, which are vector functions, and then in one specific point, those vectors are linearly dependent, does it mean that they will be linearly dependent in every point? I mean, if we don't know that they are exactly the solutions of the D, what would you expect, that they would be linearly dependent in every point? Not necessarily, yeah, because if you have two functions, for example, I can write here two functions. So we have v1 of t let's say that I will draw V1 of t and V2 of t. So they are linearly, for some t naught, they are linearly independent. But V1 of t and V2 of t can change, and suddenly for some other t, they can become linearly dependent. So for example, for some other t, this could be V1 of t1, and then this could be in the same on the same line V2 of t1. So here V1 t1 and V2 t1 are linearly dependent. But for some other point, V1 of t naught and V2 of t naught are linearly independent. So from the linear dependence in one point, we cannot just infer that the functions V1 of t and V2 of t are linearly dependent. So the question to this, the answer to this question 3 is no. Okay, but it turns out for if x1 up to xn are exactly the solutions of the nth order linear differential equations, it turns out that those are the same. So the answer is yes. The answer to this question 3 is yes. But if x1 up to xn are solutions to our dE, then if determinant of the Wronskian is 0 in some point, then it is 0 in all other points of our interval. And this is the crucial theorem in the theory of nth order differential equations, because it means that when we solve a differential equation and have some initial condition in some point t naught, we only need to check if the determinant of the Wronskian is non-zero. If this is true, then we really obtained all the solutions to our dE. But if the determinant of the Wronskian is 0, then it means that we didn't obtain all solutions. So we should check for other solutions as well. So this means that if if we solve the dE with initial condition x of t naught is something, so x prime of t naught is something. So here I mean x vector of x, I mean that we have conditions on x, and then x prime, x double prime, and so on. So we have n-1 conditions, n conditions. And if we find n solutions and then compute the determinant of the Wronskian, and if it's non-zero, then we really obtained all solutions to our differential equation without this initial condition. And determinant of the Wronskian is non-zero, then we obtained all solutions to our DE. Otherwise, some are missing. So to conclude this first hour, I would like to show you at least the idea of the proof of this theorem, because it's nice. It nicely uniforms the linear algebra and what we already know from linear differential equations. It's quite technical, but there are two ingredients. From linear algebra, we have to know what's the definition of the determinant and some properties of the determinant. And from solving differential equations, we only need to know how to solve first order differential equations with separation of variables. We will in fact be able to explicitly say what's the determinant of this W of t. So in the proof, we will determine explicitly what is this determinant of the Wronskian. And I would like to show you this proof. You don't need to know this proof by heart for the exam, but it's nice that you see it once. And then we do a break. Okay, so let's recall we have this Wronskian. This is a matrix with n columns. In first column, we have x1, x1 prime, up to x1 n minus first derivative, then x2, x2 prime, and so on. xn, xn prime, and so on. Do you remember how to compute the determinant of the matrix? How is the determinant of the matrix defined? What's the definition of the determinant? We have a matrix. We have to, we go into the first row. We choose one entry, for example, x1. And then we go into the second row. We choose one entry, but it shouldn't be in the same column as x1 from the first row. So for example, we choose x1. Then we go into the, and then the first column is not allowed anymore. And we go in the second row and we can choose one of the elements remaining. For example, we choose x2 prime. And the second column is not allowed anymore. We go in the third row and choose one of the entries which are allowed, and so on. So we do a product of numbers. We do a product of entries where in each row and each column, we should choose precisely one entry. And we do the sum of such products where we go all permutations of numbers 1 to n. So we have x1 times x2 prime, or let me rather write this for a general matrix. So we have matrix A, I, J. And the determinant of this matrix, it is A11, A22, A33, and so on, ANN. This is the product of diagonal entries. And then we have to plus, let's say, A11, and then we choose, instead of A22, we choose A23, and then in the third row, we choose A32, and so on, A44, and so on. We should go all possible permutations of the numbers 1 to n. So we do a permutation of the numbers 1 to n. The element on the first place tells us which number from the first row we should take. Then the element in the second place tells us which number from the second row we should take, and so on up to nth row. So here we have at the end, for example, an1. From the first row we take nth column. Then from the second row we take n minus first column, and so on. From the last row we take first column. How many summands are there? We should go over all possible choices of one element from the first row, one element from the second row, one element from the last row, and none of them should be in the same column. How many choices we have? Sorry? N factorial, yes. Yeah. So in the first column we have, in the first row we have n choices, then in the second we have n minus 1, and so on. So n factorial summands. And here, so each of these summands corresponds to one permutation. So the permutation, we have sigma is a permutation of the numbers 1 to n. So permutation. So for each permutation, we have a corresponding summand. Summand in the determinant. And do you remember the signature of the permutation from discrete mathematics? What is the signature of the permutation? So each permutation can be written as the product of transpositions, and the parity of transpositions tells us whether the signature is 1 if the parity is even, and the signature is -1 if the parity is odd. So signature of the permutation is either 1 or -1. So if even permutations have signature 1 and odd permutations have signature -1. So here we also have to add the signatures of the corresponding permutations in the determinant. So here we have times the signature of the permutation in each of these summand. We either sum or subtract the summand. Is this the definition you know from linear algebra? Do you recall this definition of the determinant? No. So how did you define the determinant? Okay. Usually the determinant is defined in this way, and then there are techniques to show that the determinant can be computed by some row, by deriving according to some row or according to some column. But if you don't know this formula, maybe this proof will be too technical for you. So yeah, you have to know this formula. This is the formula for the determinant. Yeah, you have to take the derivative of this formula and then use some properties of the determinant. So I thought that you know this formula. So maybe let's just skip this proof. So I will only show you. So if you don't need to know every step of this proof, but if phi is the determinant of the de Vronskian, then this calculation above shows that phi prime of t satisfies phi prime of t is minus an minus 1 of t times phi of t. So this is the content of this calculation. So the content of the calculation above is that phi satisfies star, this differential equation star. Okay, let's assume that we believe this calculation that phi really satisfies this star, this differential equation star. And now my question is, do you know how to solve this differential equation star? You don't need to know anything about phi. This boils down to what we know for differential equations. So how to solve this star? Yes, separation of the variable. So it's separable dE, and let's solve it. D phi over phi is equal to minus an minus 1 of t dt. We integrate both sides, and what we get is that logarithm of phi, the logarithm of absolute value of phi is e to the integral of minus an minus 1 of t dt. Sorry, logarithm of, this is already without logarithm. So phi, logarithm of phi is this integral on the right hand side, and if we get rid of the logarithm, we get that absolute value of phi is e to this integral of minus an minus 1, and then times some constant. And since we introduce this constant, we can also get rid of the absolute value because it's absorbed in this constant. So this is the solution. This Wronskian is in fact of this form, and this already proves our theorem. So if phi of t naught is 0, what does it mean from this formula? K is 0, and if k is 0, so phi of t is then constantly equal to 0 for every t. But if phi of t naught is not 0, then k is not 0, and phi of t cannot be 0 for any t. So this proves our theorem. If the determinant of the Wronskian is 0 in some point, then it's 0 in every other point. Okay, so the calculation above, this is only the calculation which with which you show this relation of the Wronskian, so that it really satisfies the differential equation. So here, this is the definition of the determinant, and you take the derivative, and the derivative is just computed here by product rule. So you have here you have product of functions, and when you take the derivative, you have to take the derivative of each of the functions in the product in sum over all possibilities, and yeah, and it turns out that phi prime satisfies this differential equation. So let's stop for the first hour. At this point, are there any questions? Okay, not in the classroom, maybe on the chat. Okay, let's do a 15-minute break, and the last hour will be also 15 minutes shorter because we didn't do 2 breaks.